Since N-acetylcysteine or NAC is often used as a biofilm disruptor in gut protocols, is it possible that long-term use could cause damage to the mucus layer of the gut?
This is a clip from a live Q&A session open to CMJ MasterPass members. In addition to this episode, you can access lots of other free samples from these sessions at the first link in the description.
The winner of the question contest for this month's AMA is from Melissa Malam with 39 votes. And her question is, NAC, or NAC, that is N-acetylcysteine, is often used as a biofilm disruptor in gut protocols. Is it possible that long-term use could cause damage to the mucus layer of the gut? So let's start by briefly defining what a biofilm is. A biofilm is a complex extracellular network of polysaccharides and glycoproteins. Polysaccharides are complex sugar-based structures, and glycoproteins are complex structures made from sugars and proteins. And these are assembled in a way that will protect bacteria from destructive forces in their environment. Now, when you have an infection, you might not think of yourself as the environment for the microbe, but the microbe does, and to the extent it thinks. And part of what the biofilm is protecting the bacterium from is your immune system, but it's also protecting the bacterium from other things that might infect it. So other elements of your microbiome might try to eliminate it, or viruses that are floating around might try to infect it, or you may take an antibiotic and you may want the antibiotic to kill the bacteria, but the bacteria doesn't want the antibiotic to do that, and so on. And so these biofilms are protective structures for colonies of bacteria. Now, it should be noted that normal, healthy gut microbiota colonize the mucus coating of our gastrointestinal tract, which itself serves as a biofilm for them. Okay, so the first thing we have to understand is biofilms are not bad. Biofilms are ubiquitous. They're ubiquitous, meaning you'll find them everywhere, but they're not ubiquitous in the sense that all bacteria need biofilms to survive. So what you'll find in the normal human microbiota is that there's one compartment of the bacteria that are in the lumen of the GI tract, meaning in the open space that's continuous with, from mouth to anus. And then there's a whole other collection of bacteria that are in the biofilm of our mucous membrane. And we don't want to destroy that biofilm because that biofilm is our mucous membrane. Right? So we can't be anti-biofilm except in a narrow strategic sense. Now, N-acetylcysteine, which is a derivative of the amino acid cysteine, which is one of the two sulfur amino acids that make up our proteins. And acetylcysteine is used in medicine primarily as a precursor to glutathione, which is a tripeptide, meaning a molecule made from 3 amino acids, of which cysteine is one of them, and is often limiting. And you may often see discussions that cysteine is the limiting amino acid for glutathione. That's not quite correct. It is generally the limiting amino acid for glutathione synthesis until you supply the cysteine, at which point glycine becomes limiting. Glutamate is the third amino acid when you put it together, it's actually the first amino acid, but it's the third out of the ones I'm mentioning. And glutamate can be limiting in a severely catabolic state or a severely protein deficient state, but glutamate is the most abundant amino acid in the diet, so it's very rarely limiting for glutathione synthesis. Usually if you have poor glutamate status, you also have poor cysteine and glycine status, I suppose hyperammonemia is another case where glutamate could become limiting, because in that case, all your free glutamate, you'll be using it to mop up the ammonia to protect yourself from the ammonia. But that's a tangent. So for our purposes, the reason we care about N-acetylcysteine is because cysteine as a sulfur amino acid has a thiol group, which is the same thing as a sulfhydryl group. This is an atom of sulfur connected to an atom of hydrogen. If you look at the abbreviations in a chemical structure, it'll be SH. And that's why it's called sulfhydryl. It's also called a thiol group because in chemistry, ol, that as a suffix denotes an alcohol. So ethanol in the alcohol that we drink is an alcohol. A thiol is the analog of an alcohol where you replace the oxygen with sulfur. And so an alcohol group is OH. A thiol, with thi comes from the Greek word for sulfur. A thiol group is SH. So it's OH, SH. It's the same thing as an alcohol group, except you replace the oxygen with sulfur. You take the Greek root for sulfur, and you take the ol from an alcohol, and you call it thiol. Now, this is exactly why cysteine is used in the synthesis of glutathione, because the thiol group is the reactive component of glutathione that makes it an antioxidant and that makes it capable of detoxifying things. Now, another aspect of that is that if you look at where glutathione is distributed in the body, it's mostly intracellular, but in the lungs, there's a huge amount of extracellular glutathione. And what is it doing there? One of the things it's doing there is it's interacting with nitric oxide to act as a bronchodilator. But another thing that it's doing there is that it is making mucus fluid. And when the mucus is not fluid enough, we become congested. But when the mucus is fluid, it is better able to do its job. And if we do need to cough some up, it's easier to cough up. So we want a certain degree of fluidity. Now, why does glutathione make mucus fluid? Well, this is very relevant to why NAC can be used as a mucolytic agent or a biofilm disrupting agent. So glutathione, because it has a reduced thiol group, meaning SH, is able to reduce oxidized disulfide bonds between mucus proteins. So mucus proteins are proteoglycans, like we would find in a biofilm, and they stick to each other because they have sulfhydryl groups like glutathione does, but in the highly oxidized environment outside cells, those sulfur groups tend to oxidize, which means they lose their H. SH loses its H. It loses an electron. It's hungry to find another electron. What do you do when you lose electrons? Things bind together and share electrons in a covalent bond. And so if the SH is losing their H and their electron, then two of them will find each other and say, hey, let's share an electron, and they stick together in a disulfide bond. Glutathione can come and say, hey, I got an electron. You don't have to share it with him and stick together with him. I'll just give it to you. And then boom, you can go do your own thing. And so the more glutathione reduces the disulfide bonds in mucus proteins by being the donor of an electron, the less they have to stick together. If the mucus proteins are not sticking together, they are thinner, they are more fluid, and they do their job better to a certain extent. Now, in an oxidizing environment, you can glutathionylate proteins. And in fact, you do glutathionylate proteins. And so under oxidizing conditions, and then also perhaps in a strong excess of glutathione, you could probably have glutathione actually bind in a disulfide bond to a mucus protein and render it non-functional. And I say this only to use as a mental model how an excess of NAC or NAC or NAC's behavior in a highly oxidizing environment could potentially do something different than what you would want it to do. Okay, now all that said, NAC, N-acetylcysteine, NAC, acts as a mucolytic because it doesn't have to become part of the glutathione molecule to do that, because it is the part, or cysteine is the part of the glutathione molecule that has the thiol group. So cysteine on its own has the thiol group. And acetylcysteine, NAC, has the thiol group. So you can use NAC to increase glutathione, and glutathione will act as a mucolytic agent, but NAC on its own will also act as a mucolytic agent. So you can deliver NAC directly to mucus layers in the body, and before it's even capable of being absorbed and broken down and by deacetylation and then used to synthesize glutathione, before any of that happens, NAC will act as an immediate mucolytic. Now, because biofilms can use our mucus proteins, or may even be our mucus proteins, NAC can disrupt those biofilms by breaking disulfide bonds. Now, there are many bacteria, okay? And everyone knows this. As many types as there are of biofilm-loving bacteria, there are different types of biofilms. So it's not like every biofilm is made of X. It's this bacteria has this biofilm, that bacteria has that biofilm. They all have different strategies for how they make their biofilms. Now, just to give you one example, the soil bacterium B. subtilis has a biofilm where it has been shown that the main components of the biofilm formation do not require disulfide bonds. However, there is a protein in the biofilm that must make disulfide bonds in order to make the biofilm hydrophobic, which means afraid of water, which means fat soluble and not water soluble. And why is that significant? Because generally this biofilm is going to be in an aqueous environment, such as the soil, where there's water running through it, or in our gastrointestinal tract, where everything we're eating has water in it, and then we drink water on top of it, we drink other things that have water in it. Our whole bodies are overwhelmingly made of water. And most stuff that might be able to hurt that bacterium will be coming via water, right? Like even gastric juice is primarily made of water. And so that could be a part of the B. subtilis biofilm that protects it from things that could hurt it that may come through, like an antibiotic. Of course, many people, and I think this is probably true, see B. subtilis is actually beneficial in humans, so you don't want to kill it with an antibiotic. But it would help you to kill it with an antibiotic if you have a disulfide bond breaking agent, because not only may you thin the mucus layer that perhaps it may be using when it's in a human GI tract, but you can specifically break apart its hydrophobicity to make water be able to penetrate the biofilm and thereby bring things that are water soluble that might kill the B. subtilis. So I come back to this idea that we don't want to be anti-biofilm, because we have beneficial bugs that are using biofilms, and NAC has no brain. And so NAC NAC has no computer software. So NAC can't go in and be like, which biofilm did you want me to disrupt? It will just go in and break disulfide bonds wherever they are. Now, that's not a bad thing either, because again, we have an abundance of glutathione in many areas, but especially in certain mucous membranes like the lung, the extracellular fluid of the lung, where we want it to regulate the fluidity of mucus, and we don't want infinitely disulfide bonded mucus, which is very rigid and not properly functional. So it's about balance. Now, another thing I'll say is that conceivably, at a theoretical level, I believe it is plausible that at a certain dose of NAC, you are going to thin the mucus and make it more fluid, but you're not going to deplete it. Whereas at a higher dose of NAC, especially in an unusually oxidative environment where perhaps you have a lot of oxidative stress going on in the GI tract, I think under those conditions, you could probably deplete mucus proteins by binding, the NAC can N-acetylcysteinolate a mucus protein under those conditions, which would effectively be rendering them non-functional. So I do think there's going to be a dose response as well as a context dependency here. Now, according to a systematic review that was published a few years ago, there were at that time 8 trials. This was in 2014, and it's N-acetylcysteine is a powerful molecule to destroy bacterial biofilms, a systematic review. And in that paper, there were 8 studies, and there have since been a few more, showing that N-acetylcysteine can disrupt biofilms, and that can help render antibiotics more functional against things that you want them to destroy, such as H. pylori. Now, let me share this table with you from that paper. And one of the things that you can see in this table is if you look at biological effects, you have reduction of gastric barrier mucus thickness, reduction of mucus viscoelasticity, reduction of gastric barrier mucus thickness, increased permeability of antibiotics, eradication of preformed biofilms, overcoming antibiotic resistance, which is interesting. Perhaps biofilms are playing a role in antibiotic resistance in a structural way, and that's not just a phenomenon that we usually think of selection for the resistant bacteria using the antibiotic. Reduction of mucus viscoelasticity, increased permeability of antibiotics, eradication of mature biofilms, inhibition of biofilm production, eradication of preformed mature biofilms, demolition of biofilm. Demolition is a funny word in this context. Now, this is, and you can see that there's more studies of H. pylori than anything else, but there's also quite a few of strep aureus. We've got S. pyogenes, S. pneumoniae, S. influenzae, S. epidermidis, which is the natural colonist of the skin, definitely a good bacteria. E. coli, and P. vulgaris, which is acne related. Numerous different bacterial biofilms. And what does that tell you? Well, it tells you that this is a highly non-specific event, non-specific effect. Now, the other thing that is a little concerning about that table is there's just a general non-specific reduction in the thickness and viscoelasticity of the mucus layers. Now, it's great if you in the acute sense where you're trying to kill H. pylori, because it allows you to access the H. pylori that's hiding in the mucus. Do you want that to be chronically reduced? I'm not so sure about that. It sounds like something that could be pro-ulceration, for example, because what happens in an ulcer? Well, one of the things that happens is you deplete the mucus layer down to the raw stuff underneath, and we don't like that. So I looked for studies on whether NAC can cause ulcers, and it looks to me like NAC can probably cause ulcers at extremely high doses based on animal experiments, but that you can get pretty high doses of NAC for at least a couple months into humans, and the rate of GI side effects has to be very, very low. So let's take a brief look at some of those studies. So I should mention, by the way, in that table, it didn't list in the table that you were helping with the clinical condition, but I pulled some of those studies, and it also, that review talks about the results in the text. And so one of them found that 1,200 milligrams of NAC twice a day for 9 days improved the ability of antibiotics to eradicate H. pylori. Another one found similar results with 400 milligrams 3 times a day for 10 days. So that's 1,200 milligrams per day. And then another study used pretty similar doses, and it was 600 milligrams. Oh, actually lower dose, 600 milligrams a day for 1 week. And I was only able to access the full text of that one. And at 600 milligrams per day for 1 week, there were no more adverse effects with NAC than with the placebo. I couldn't access the full text of several of the others. One of them was in the German language. One of the other, I just couldn't get through the usual channels in the time that we had to prepare, or that I had to prepare for this. But I think there's another study that many people have looked at that I think is even more valuable in terms of GI side effects with NAC not happening. And we'll talk about that one in a second. But first, I want to go through 3 animal studies that I pulled that looked pretty relevant. This is not comprehensive, but I was just looking for animal studies that looked at whether NAC could cause or prevent or protect against ulcers. So I'll give you 2 that show that it's protective and 1 that shows that it causes ulcers. So the first one is called Protective Effect of N-acetylcysteine Against Ethanol-Induced Gastric Ulcer, a pharmacological assessment in mice. They used 100 to 500 milligrams per kilogram body weight for 7 days prior to inducing ulcers with ethanol, and found that the NAC protected against the ethanol. Second one's called N-acetylcysteine as a possible protector against indomethacin-induced peptic ulcer, crosstalk between antioxidant, anti-inflammatory, and anti-apoptotic mechanisms. Indomethacin is a non-steroidal anti-inflammatory drug, or NSAID, that inhibits COX and thereby destroys the gut. And they used 300 to 500 mg per kg for 5 days before they induced the ulcers with an NSAID, and specifically indomethacin, and they also found it protective. Now, on the other hand, there is a rat study that showed that NAC straight up caused ulcers in animals that were not stressed in any way. And this is called effects of verapamil, carbenoxolone, and N-acetylcysteine on gastric wall mucus and ulceration in stressed rats. Now, although the title says it's in stressed rats, when you look at the study, they had stressed rats and non-stressed rats as controls. And even in the control rats, NAC just straight up depleted the gastric mucus and caused ulcers with no other stressor. Now, what dose did they use? They used 1.5 grams. So this is 3 times the max dose in the other 2 studies per kilogram body weight. Now, when you're looking at a body weight adjusted dose in mice, you have to cut the dose down by 12 before you translate it into human dose to adjust for surface area. This study was done in rats, not mice, and in that case, you adjust for surface area by dividing by 6. So if you take the standard 70 kilogram reference man, it's now outdated because everyone is fat. But if you just use the 70 kilogram reference man to adjust by body weight, and you also divide by 6 in order to adjust for the surface area difference between rats and humans, this is the equivalent of a human taking 17.5 grams of NAC. Now you say, per what? Well, in this study, they just gave a single dose, and then 2 hours later, they killed the animal and they looked at how much gastric wall mucus was there and what was the degree. They created an ulceration index to quantify, were there ulcers, how many ulcers were there, and how bad were they. And the ulceration in the gastric wall mucus was decimated, and the ulceration index was raised, showing that a single dose of 17.5 grams of a single dose of the body weight and surface area adjusted human equivalent of taking 17.5 grams per in a single dose 2 hours later has caused ulcers. So, you can make the point that, well, Was it a sex difference, a species difference, or a model difference because the NAC was protecting against ethanol and NSAIDs, but on its own? Like, how can it be model dependent when you don't really have a model except the NAC in the study where it's harmful, right? So, you could, but I guess what you could say is maybe if you're an alcoholic, you should take NAC to prevent ulcers. But if you're not an alcoholic, maybe NAC would cause ulcers compared to not taking NAC. I mean, that's possible. But I think that it's the simplest thing to do is to say it's a dose difference. Now, we do have to take into account that I think both the other studies were in mice. Let me make sure that that's true real quick. No, okay, they weren't. That's not true. So just controlling for surface area by looking at the 2 rat studies, the one that found NAC is protective used a max dose of 500 mg per kg body weight, and the one that found that it directly causes ulcers used a single dose of 1.5 grams per kg body weight. So it's a 3-fold difference in dose. So basically, it looks like it's not cumulative because in the dose where NAC was protective, it was the highest dose was 500 mg per kg for 5 days. And so 500 mg per kg 5 days in a row is a total of 2.5 grams per kg. So the total dose in the study where NAC was harmful was 1.5 grams per kg, and the total dose in the study where it was protective against indomethacin was 2.5 grams per kg. So it's not about the cumulative dosing. I realize it's a very limited data set, but my view is it's not about the cumulative dosing. It's about the acute dosing, which fits exactly with what I said at the outset, which is that the general effect of reduced thiols will be to reduce the thiols in the mucus proteins or the other biofilm components so that they don't form disulfide bonds. But you would expect that if you had a high enough concentration, you could, by mass action, meaning by the sheer force of the presence of so many NAC molecules, you could drive NAC sticking to the mucus proteins and rendering them non-functional. So I think that's what's happening. I think it is dependent on the acute single dose, where at a low dose in any given unit of time, you are just making the mucus more fluid. And, you want a certain normal amount of fluidity. It's not like you want to max it out when you're not trying to penetrate through it to kill H. pylori or something like that. But I don't think you're going to deplete the mucus and make an ulcer or do other harm by depleting mucus through cumulative dosing of doses that otherwise are just making the mucus more fluid. I think you will just make the mucus more fluid and keep it more fluid. Now, you might keep it more fluid than it should be if you take the NAC in perpetuity, but I don't think you're going to deplete it. That's my perspective, because I think with the limited data set, looking at those animal studies, I think it fits in perfectly with the model I gave you based on chemistry. Now, I think the most relevant human study to look at, not that there aren't many human studies with NAC, but I think the most valuable one is just driven by, as far as I know, this is the highest dose NAC for the longest period of time study in humans. And this is glycine and N-acetylcysteine, in parentheses, GlyNAC. Supplementation, older adults, improves glutathione deficiency, oxidative stress, mitochondrial dysfunction, inflammation, insulin resistance, endothelial dysfunction, genotoxicity, muscle strength, and cognition. Results of a pilot clinical trial by authors known as people who can't summarize in a title. So in this paper, they supplemented for 10 grams of NAC per day, and obnoxiously, they do not say how it was dosed. So was this 10 grams at once, or was this 3.3 grams with each meal or what, right? Because in my model for thinking about this, that makes or breaks the whole point, right? Because I think 10 grams and a single dose is more than halfway to the 17.5 gram human equivalent of the rat dose that in 2 hours caused ulcers. But they don't say. So I'm going to assume, because I would have done it this way, that this was in 3 divided doses. In any case, 10 grams of NAC per day, granted it's with 7.5 grams of glycine, granted it's not randomized, it's not controlled, but in 8 older adults and 8 younger adults, who you would not have known about if you just looked at the title, but the 8 young adults are hidden in the method section, for 24 weeks, found that they specifically asked them if they had GI side effects, and no one said yes. And no one dropped out of the study for any reason. So, there's 16 people in this study. And so if you divide 100 by 16, you've got 6.25. So basically, if the rate of GI side effects from 10 grams per day of NAC for 24 weeks from this study is accurate or precise, neither of which are likely to be true because there's only 16 people in it, but using what we have, that basically means that if there are people who develop GI side effects from 10 grams of NAC per day for 24 weeks, it has to be fewer than 1 in 6 people. Now, 1 in 7 people is not very rare, so I wouldn't read too much into this, except to say that it is at least not the normal predictable consequence of 10 grams of NAC per day taken for 24 weeks to get GI side effects from it. Now, does that mean it's not doing anything negative to the GI tract? I wouldn't go so far so fast. So first of all, we don't know jack about NAC metabolism, despite what you might find claimed on the internet. We really don't know jack. And part of the reason we don't know jack is because there is a preposterous belief among people that study absorption of stuff that you don't have to measure fecal content of the thing that you measured. And they just systematically believe in the scientific literature that you can just measure the plasma response to something and judge its absorption, or that you can measure plasma in urine and judge its absorption, which is asinine. And so we actually don't know jack about the absorption of almost anything as a result of this. But one of the things that you'll see debated in the literature on NAC is that human studies that just look at plasma, for some reason, human researchers, they don't want to deal with human feces, but like rodent researchers deal with rodent feces all the time. I guess they're just used to it. Like the rats poop in a cage, so you can either throw it away or use it for something, but humans don't poop in your office unless you ask them to. And so I guess people who work with humans, they just don't like dealing with poop. It's like riding first class or something if you do human studies. I don't know. But anyway, so, classically, as expected, the animal studies of NAC measure fecal content and the human studies of NAC never do, right? So you get these studies in humans where they say only 6 to 10% of NAC is absorbed because that's what appears in the plasma and the urine. And then you got animal studies saying 97% of NAC is absorbed because only 3% occurs in the feces. So if you want to synthesize this, the way that you could do it, not that everything works out the way you want it to do when you don't actually measure what you're interested in, but if you wanted to make something up because it fits the data, rather than measuring it, which is what they should have done, you could say that 3% of NAC winds up in the feces, 6 to 10% of NAC winds up going through the plasma at some point. And, that accounts for 9 to 13%. And so 87 to 89% of NAC is eaten up by the enterocytes in the intestines. Like maybe that's what happens. But the point is no one really knows in humans particularly. And so therefore we don't know how much sulfur that's delivering to the gut microbiota and how much sulfur would be metabolized by them and thereby cause disproportionate overgrowth of sulfur reducing bacteria, which can do a number on you. It's not something that you want. So I would have that concern. Then on top of that, as we said before, the normal healthy microbiota, a portion of it, lives in biofilm. And so if you're chronically blasting yourself with a dose of NAC that is, let's see, 600 mgs a day disrupts biofilm. So you're constantly blasting yourself with, what is this? Got to put 0.6. With 17 times the amount of NAC that's needed to disrupt biofilms, you're going to have very exceedingly fluid mucus and very poor biofilm formation for your normal microbiota. It's got to be the case. And so even though the evidence is against there being a greater than 1 in 7 incidence of GI side effects in people, I think the evidence is wholly inadequate to know whether there are subtle microbiome distortions that are not good that are caused by high-dose NAC. So therefore, my conclusion is that NAC at high doses up to 10 grams chronically for up to 24 weeks is not going to deplete your gastric mucus to the or intestinal mucus to the point where you get ulcerations, or even to the point where you have a higher than 1 in 7 rate of GI complaints. However, it will absolutely bias your mucus and natural biofilms to a thinner mucus state and a biofilm disrupted state. And between that and the delivery of sulfur to the microbiome in excess quantities, I think both of those pose risks to microbiome distortions. And, so therefore I wouldn't use NAC unless you have a targeted purpose for it. And maybe that is, if it's to deal with biofilms, you shouldn't need, the doses used to disrupt biofilms are 600 to 2400 mgs per day for 5 to 7 days, basically 5 to 10 days. So you shouldn't need to use it chronically. And I think the harms are more likely to be mediated by very high doses. If you were to take 10 grams for doing that whole list of things in the title in older adults there, I would spread it out across the day, but I wouldn't be doing that unless I had a very specific targeted reason. And I think even in that study, they don't have a specific targeted reason. They're using it as a generic, oxidative stress is increased in old people. Let's find an antioxidant, throw it into the mix. I get it increased glutathione, but the rationale for the dose and the particular strategy is not that well thought out, and it's not individualized to the person at all. So I would not do high dose NAC for long periods of time. I would not do high dose any supplement for long periods of time unless I had a specific, individualized to me reason to do it, because there's always, despite the possibility of huge benefits to supplementing when you do need it, there are always unknowns in what kind of imbalances you could create. So, the TLDR, the TLDL or TLDW for the, this, so it's a video and a podcast. of this is 600 to 2400 mgs max per day, always spread out in divided doses for 5 to 10 days can disrupt biofilms. You should not need more than that, and you should not need longer for that. If you have some other reason to use high-dose NAC, 10 grams per day spread out across the day, I'm assuming and recommending, for up to 24 weeks has been shown to be safe in 16 people and therefore does not have a higher than 1 in 7 rate of side effects. But again, don't take high dose anything if you don't need to. All right, that is the winning question.
This is a clip from a live Q&A session open to CMJ MasterPass members. In addition to this episode, you can access lots of other free samples from these sessions at the first link in the description. If you want to become a MasterPass member so that you can participate in the next live Q&A, or so that you can have access to the complete recording and transcript of each Q&A session, you can join at chrismasterjohnphd.com/masterpass. You can save 10% off the subscription price for as long as you remain a member by signing up at chrismasterjohnphd.substack.com/Q&A. That's Q&A spelled out as Q-A-N-D-A. These links are in the description.